thanks everyone for being here. I would like to present today. I'm joined to work with Nicolas Charon, who is here, and also with Martin Bauer from Florida State on inexact shape matching in the square root normal field framework. And to say in a couple of sentences what this is all about, it's about elastic matching of shapes, so the shape correspondence problem for unparameterized curves and surfaces. And I will present both a new mathematical formulation and then an algorithmical numerical implementation of this problem. Methodologically, this will combine the theory or the tools of square root normal fields and of variable distances. And the resulting algorithm actually works pretty nicely. It's fast, can be implemented easily. It's quite general in that it applies to different meshes and different topologies, and it also allows one to account for texture information. What the result is in the end, just to give you a visual impression of this, is a point correspondence. So what you can see in the left picture here is two hands that are matched to each other, so you find corresponding points between these surfaces. And in addition, you also get a distance between these two shapes, in this case these two hands. And if you have an entire data set of such shapes, you can calculate a matrix of pairwise distances, which is what you see on the right image. And this can then be used in further processing stages for shape analysis. So you could apply some for example, machine learning or clustering algorithms to this distance matrix to extract further information. And that's kind of the goal of this entire exercise. So what I'm going to present today is first a little bit of background material, and that's mostly to settle the notation because the algorithm or the method that I'm going to present draws on three different strands of literature that I need to briefly talk about. And then I'm going to show you some the algorithm itself, some comments about the implementation, some numerical results, and a little bit of discussion. So the first theoretical part that this algorithm draws upon is elastic shape analysis. And elastic shape analysis more or less is, mathematically speaking, Riemannian geometry on shape spaces where the Riemannian metric has an interpretation as an elastic deformation energy. So you start to look at your shape space of interest. In the context of the present talk, this will be a set of immersed surfaces. So you give yourself a manifold M. In this talk, it will always be a compact manifold M and also an orientable one. Think of a sphere or a unit circle. And you look at immersions of that manifold into Euclidean space. And we'll deal always with immersions of also of codimension 1. M will be a d-1 dimensional manifold. And on this then Fréchet manifold of immersions, I start with a Riemannian metric. And this Riemannian metric, we will see several examples later on, can be seen as something that measures the length of an infinitesimal deformation of the shape. And the use of this metric is to define Riemannian distances between given shapes via the Riemannian path length functional. So the definition of this path length function is right here. You look at curves connecting two given shapes. So a curve in shape space is kind of a deformation, a continuous morph of the shapes. And you measure the length of this morph or of this curve in shape space using the Riemannian metric, and this gives you a distance functional that you use then for this later processing and for shape analysis. So that's kind of the framework, the overall framework that I'm going to be operating in. And numerically, what one has to do to calculate these distances is somehow solve this optimization problem, this minimization over the set of curves. And this can be done, as is well known, by path straightening or geodesic shooting methods, which are, however, quite costly numerically. So it's very interesting to investigate different directions of how this problem can be simplified. And one way of going about this is to find or construct isometries to some simpler spaces where the geodesic boundary value problem can be computed more efficiently. Now, one way of constructing such isometries and the corresponding Riemannian metrics is via so-called square root normal fields. And what I'm showing you here is a rather general formulation of this framework where we look at parameterized shapes. So recall it's just another name for an immersion. I have a parameterized shape f, and I define the corresponding square root normal field as the unit normal field n multiplied by the Riemannian half density on the space. Now the result is that, and that's exactly why I constructed it this way, that these half densities, these vector valued half densities, form a Hilbert space. So I can just take two of these vector valued half densities, take the contract the vector valued part and integrate over m, and I get a real number. Now if I change this recipe a little bit and I differentiate before this integration, then I can construct a Riemannian metric out of this, and that's what's written down in the second bullet point, where I associate to the square root normal map a Riemannian metric by first taking variations of the surface f, or of the immersion of the shape f, in some directions h and k, and then I perform my integration. So now I've constructed a Riemannian metric. It might actually be only a pseudo-metric, but for the purpose of this talk I'm just going to call it a metric. It might have a kernel, but this won't pose any serious problem. What I would like to mention briefly is that this is a first order Sobolev metric, and there's a lot of literature on this. Now the main advantage of this construction is that now this square root normal field is a Riemannian isometry. It's an isometry between Riemannian manifolds. And I can use this isometry to construct a numerically very cheap, and by that I mean just efficiently to compute, approximation of the Riemannian distance function. So what do? I have two surfaces, f1 and f2. I calculate the square root normal field of the surface f1, square root normal field of the surface f2, compute the L2 distance between these vector valued half densities, and that's it. That gives me a first order approximation of the distance. So this is great news, because this allows me to very efficiently compute at least approximatively these distances on the space of parameterized shapes. Now if I want to pass to the space of unparameterized shapes, and I'm going to say in a moment what that is, then I need a third auxiliary tool, namely a third kind of distance on the set of unparameterized shapes. And so this will be the third ingredient of my kind of background and notation part. These are varifold distances. So unparameterized shapes are just shapes modulo reparameterization. So I have my manifold M. I can look at a diffeomorphism group of M, and this group acts from the right on the set of immersions, on the set of parameterized shapes. And the corresponding quotient space is the space of unparameterized shapes, and I denote its element by like equivalence classes of f in square brackets. It's not so easy to construct distances on this quotient space that are quickly and easily computable, but varifold distances are one great exception to this. They are distances of the following form. You start with a kernel rho and a kernel gamma, and they need to satisfy certain properties. But then what you do with them is use the kernel rho to measure the distance between the positions of these surfaces. So it's like f1 of x1 minus f2 of x2, squared distance, and then I apply the kernel rho. And similarly, I use my other kernel, the kernel gamma, to measure discrepancies in the normal directions of these surfaces. So here you see gamma applied to the scalar product of the normal field of f1, tested in an inner product with the normal field of f2. So that's a pretty easy recipe, and the most important property of this distance that's defined this way is that it is fully diffeomorphism invariant, which is just another way of saying that it's actually a distance on the quotient space and doesn't depend on the representatives. On the representatives. Maybe one more remark to give you like an idea of what this means to work on the quotient space from a numerical or algorithmical perspective. parameterized shapes, you can think of them as meshes, if you discretize them. And unparameterized ones is like looking at, considering two different meshes the same when they describe the same surface, kind of when the surfaces are exactly aligned to each other, but the mesh structures might still be different. So here we now have a distance on unparameterized shapes. And that's basically all that I need for the setup. I have all the ingredients together to now define a new algorithm which serves the purpose of creating, it's a matching algorithm for unparameterized shapes. It will combine square root normal fields with varifold distances, and it will kind of inherit the nice properties of both. So varifold distances are really easy to compute, but geometrically they have the drawback that they do not have an elastic interpretation. And to kind of underline this a little bit, let me say that geodesics in varifold space are straight lines in a space of signed measures. So it's like you have one surface and another surface, and you look at them actually as kind of measures, and then you blend one surface out while blending the other surface in, and that's the shortest connection between the two. So geometrically, that's not a very natural way of interpolating between two given surfaces. So somehow we want to move away from this distance and define a new and meaningful distance, but still retain some computational speed or computational efficiency. So here is the algorithm that we propose. We want to match two surfaces f0 and f1. The functional that we're going to minimize in the end is a sum of an energy functional of two terms. The first term measures a deformation energy, and the second term enforces in a relaxed way the boundary condition that somehow the free variable f, which is like the shape, it's kind of the, I want to match f0 to f1 using f. So f will be f should be in the same equivalence class as f1, and I'm relaxing this constraint using a Lagrange multiplier. So this is like the second term which enforces the boundary condition, and the first term, ideally I would like to put some kind of H1 or Sobolev energy in there, but what I'm doing instead is I'm using the square root normal field distance, which, as we recall, is a first order approximation of it. So I've kind of modified the original geodesic boundary value problem that I wanted to solve. I've modified it in two ways. I've relaxed it, and I've approximated the deformation energy. And that's the algorithm that we're proposing. It goes back on some early ideas where varifold distances have been used in a similar way, but not in combination with square root normal fields and not in combination with these first order inner metrics. So a couple of remarks about implementation. First of all, the implementation is pretty easy because the varifold distance and the square root normal fields, they can all be defined on triangular meshes. So I can use piecewise linear curves or triangular meshes for surfaces as a discretization, and write down these energy functionals pretty much directly. And even the gradients can be computed by hand and then implemented efficiently. And in comparison to what other algorithms have been doing to try to solve the same problem, this has several advantages. Namely, we kind of implicitly optimize over the reparameterization group, whereas other algorithms had to use either dynamic programming or an explicit discretization of the reparameterization group to achieve the same goal. And this is not needed here, which kind of boosts the speed of the algorithm. And the result is an algorithm that can be implemented, or like this minimization can be done using any standard optimizer that you want. And what we did here was that we used a standard limited memory BFGS method with manually implemented gradient. Here a couple of numerical results. So first of all, as I said, we want to use this algorithm to compute distances and then maybe apply some machine learning tools to it. So here is a little example where we applied it to curves in leukemia data set. And we wanted to see how closely we can reproduce the results that you get by dynamic programming, which is one of the state-of-the-art methods for solving this shape matching problem. And actually we see very good results and comparable, so the results are comparable to the state-of-the-art, and the implementation is fast, like our implementation is fast and more general, as I will show next. Because somehow dynamic programming and also spherical harmonics, which is the explicit discretization of the renormalization group, that's restricted to special settings, whereas our setting here is actually pretty broad. To underline this by an example, I would like to show you here this geodesic interpolation between a single sphere and two spheres. This freedom of dealing with different topologies is made possible by the fact that varifold distances, which is like our data attachment term that we're using in the algorithm, they can deal with differing topologies, and so our algorithm kind of inherits these benefits. What you see in the picture are two geodesics. The top one is an interpolation between like one circle and two circles which are close together, and in the second line these two circles are moved a little bit further apart. And then you can see that this interpolating surface F, which is the colorful object, you can see the shape here. It kind of has to retain the same topology, but it does this by creating a very thin and narrow object in the middle. A further advantage, again inherited from varifold distances, is that one can deal with pretty general data attachment terms. For example, one can try to match not just shapes, but shapes with additional information that could be texture, color, or for example also some a priori like expert knowledge that you would like to incorporate when you do your matching. And the example that I'm showing here could be interpreted a little bit in this way. So on the left you can see these two shapes that should be matched with an additional binary information that then will guide the matching. And on the middle and right you can see that the differences here are not very large, but you can see that with this additional functional data information you get a match that just respects the coloring that was given a priori. And so one can guide the matching procedure in this way. Here is one slightly more elaborate example where we try to match different hand postures. This example runs in around 1 minute on a standard laptop with a GPU, despite the fact that there are like sufficiently many vertices in there, and so the algorithm scales quite well. And also thanks to this elastic deformation energy, one gets very nice shape correspondences. And by nice in this setting, I would mean just anatomically correct correspondences. The thumb is mapped to the thumb, the fingers are mapped to each other, and so on. On the lower right picture, you can see this linear homotopy between the target shape and the matched shape. The matched shape is the green one, and so you can see that these lines are kind of nicely parallel to each other, and one gets a nice match. Despite all of these advantages, let me mention still that the algorithm has some limitations, and there's a little bit of, I think, future work to be done in terms of how to deal with these problems. So one of them, I would say, is solvable, but it poses interesting geometric problems. And that's that if you run this algorithm, what you actually get is not a geodesic homotopy, but just the initial template and the matched surface. And if you want to extract a geodesic homotopy from this, you need to invert, or at least approximately invert, the square root normal field map, and there's quite a bit of literature on this, a couple of references down there, and this is actually also how we produced some of the images that I showed you before. Another limitation is that both the varifold metric and the Sobolev-1 metric are weak metrics, in the sense that the Sobolev order is rather low and the varifold distance also penalizes or like regards only directions of the surface but no higher order properties, like curvature, for example. And as a result, this algorithm does have some numerical instabilities, and just want to be honest with you, like this is what can happen if you choose your parameters maybe not in an optimal way and so on. Some of this might actually be an optimal match because the varifold distance doesn't see objects of lower dimension, like strata of low dimension are not seen by the varifold distance. So some collapses, I mean there are better examples than this, but some collapses are optimal. Yeah, and then there are some instabilities. And with this, I would like to thank you very much for your attention and end this talk. Thank you.